All right, so this is the gases unit review. I'm sorry it wasn't up earlier. I recorded it all yesterday and then realized that the sound was not on. How frustrating. So we're going to go through this. It's going to go a little quickly because this is just review, but I encourage you to email me with any questions you have. We're going to do essential skills, the kinetic molecular theory, review the butane lab, and then talk a little bit about the past unit's essential skills, since there's always review questions in the test. Essential skill number 1 is very simple. It's just STP, standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. If you do it in Kelvin, it's 273 Kelvin and 1 atmosphere. Something to remember. Essential skill number 2, the lowest possible temperature. So it's 0 Kelvin. It says lowest possible 0, but it's 0 Kelvin, which is negative 273 degrees Celsius. At this temperature, all molecular motion ceases, or all molecular motion stops. It is not 0 Celsius. That's where water freezes. That's not the lowest possible temperature. It is 0 Kelvin. Essential skill number 3, how do gases exert pressure? Collisions with the surfaces of the container or collisions with other gas molecules. That's how it exerts pressure, that quick collisions. And there's a little image there that kind of describes it, just to hope that that sticks in your memory. That you can see that it's colliding with the wall of the container, and of course in an ideal world there's no loss of energy, but regardless, if it's the real world, that also those collisions are what cause pressure. Essential skill number 4, there are 2 different ways that this question could be asked. The first way is saying that each of the gas's pressures added together gives you the P total. And you can see in the picture to the right, there are 3 containers. The first 2 containers are separate. One's hydrogen, one's helium, and they each have their separate atoms, partial pressures. The amount of pressure is in atmospheres. If you add them together, that's all you do, is just add them together. You have more moles of gas, but it's the same amount that's in the other 2, and the pressure is added up. So that's all the first part is. The second part is very similar to the lab, where the total pressure, which is the atmospheric pressure or the barometric pressure, is equal to the pressure of the gas plus the pressure of the water vapor. And the water vapor, you can see, is up here. So you have the gas being produced, kind of with it piped into the tube, into this top part, and you add them together and you get the total. The question, though, will ask you what the pressure of the gas is. The total pressure is always the atmospheric or the barometric pressure, and we'll give you that in the problem. The water vapor pressure is found in the vapor pressure table, and or we'll just tell you at 20 degrees Celsius, this is the pressure of the water. Once you have those 2 pressures, you are just subtracting the 2 pressures to get the pressure of the gas. It's just a manipulation of that equation. So it looks more complicated because it's like 3 or 4 sentences long, but all you're doing is subtracting the pressures. And quite frequently, they're in millimeters of mercury or torr. Sometimes they're in atmospheres, though. Essential skill number 5 is the combined gas law. And the way I remember it is that P1 V1 over T1 equals P2 V2 over T2. However, if you look at the red form, that's the form that will be the easiest to manipulate. So when you're solving equations, I would encourage you to have that one memorized. P1 V1 T2 is equal to P2 V2 T1. All that happened was a cross multiplication to get the t's on the opposite side, but it's a linear form, we'll call it. And so then if you remember that, everything else is a little bit easier to manipulate. The temperature is the only variable that has to be in specific units. The temperature must be in Kelvin. The pressure and volume can be in other units, but temperature must be in Kelvin. So some of the relationships, you can see Charles' law, Gay-Lussac's law, Boyle's law. Now it's important that you remember those names, but remember the relationship. That pressure and volume, it's inverse. As pressure goes down, volume goes up. And you can see that in this formula. For them to be equal to each other, if the pressure goes up, volume has to go down. However, for both volume and temperature and pressure and temperature, those are direct relationships. That when one goes up, the other one has to go up. And there were 3 activities we did. If you remember the oil plug activity, where we drew a little bit of oil into a capillary tube, and as the temperature cooled down, the volume went down. Okay, so that was that volume and temperature, that Charles law. the can crush, you could look at it a couple different ways. But when you turn the can upside down, the temperature dropped suddenly, which meant that the pressure inside dropped suddenly. The pressure outside the can remains the same, but because there's the pressure is so much lower inside, the can crushes together. So that's Gay-Lussac's law. And then the syringe had you push the plunger down and you increase the volume. You increase the pressure and the volume went down. That's that inverse relationship. Increased pressure, decreased volume, which was Boyle's law. So those three were examples of that. Might help you remember. And then finally, essential skill number 6 was the ideal gas law. PV equals nRT. You have to have these memorized. Pressure is P and has to be measured in atmospheres. If it's not in atmospheres, you have to convert it. V is volume, which is the units of liters. If it's not in liters, you have to convert it. N is the number of moles. R is the gas constant, which we encourage you to memorize, but it is on the back of the periodic table. So you see that down there, 0.0821 liters atmosphere over mole Kelvin. And finally, the temperature, which we've already mentioned before, has to be in Kelvin. So, and the units, like that'll be a question on the multiple choice, but it is on the back of the periodic table, which should be helpful. All right. And an extension of the ideal gas law is molar volume. 1 mole of any gas at all at STP has a volume of 22.4 liters. So at the bottom, I have 3 bulbs, helium, oxygen, and carbon dioxide. There's 1 mole of each of them. At STP, it's 22.4 liters. Even though the mass of each is different, the volume is the same. And that can be easy. You just have a little 2-step bridge if you're converting between moles and liters of anything. So speaking of conversions, the things that you'll need to do if you have milliliters and you need to go to liters, you're dividing by 1,000. So if you have 240 milliliters, it's 0.240 liters. You're looking at Celsius to Kelvin. You have to add 273. So if it's 25 degrees Celsius, it's 298 Kelvin. And finally, the units of pressure. There's a few different equalities there. I want you to notice that millimeters of mercury and torr are the exact same. So it's 1 to 1. So if there's 760 millimeters, it's 760 millimeters of mercury, it's 760 torr. However, if you're converting from torr or millimeters of mercury to atmospheres, you need to divide by 760, which you can see at the very bottom down there. So you need to be familiar with that. There'll be a few questions on that, and you'll have to do some conversions. The kinetic molecular theory. Now, you don't have to memorize these verbatim, but you have to know all 5. There's a multiple choice question that asks you, hey, which one is or which one isn't part of the kinetic molecular theory? And I've highlighted in pink the things that you should know. Number 2 and number 4 are not true for real gases. So a collision between particles being perfectly elastic, no loss of energy, that doesn't happen in real life. Remember the tennis ball, I dropped the tennis ball, it didn't come all the way back up to my hand. Like that's an example of the fact that our world is not perfectly elastic. And 4, gas particles are not attracted to each other. Well, that is absolutely not true. They are definitely attracted to each other. But remember that the kinetic molecular theory is about ideal gases, which are imaginary, which is why why they're using this to predict behaviors of gases. 1, 3, and 5 are true for all gases, regardless if it's real or ideal. The gas particles are tiny, they are far apart. Gas particles are always moving rapidly, randomly, and continuously. And number 5, the kinetic energy is dependent upon the temperature, because temperature is average kinetic energy. So now, speaking of the kinetic molecular theory, what's close to ideal? The question is, which gas molecules are closest to ideal, and under what conditions are they close to ideal? So we're looking at monatomic, which are noble gases, and small diatomic, so mostly the nitrogen, hydrogen, oxygen, fluorine. And the conditions that those small diatomic molecules, you don't have to know, just know that the small diatomic ones and monatomic are the ones that are closest to ideal. Low pressure, which means they have a high volume that really gets those molecules or those particles far apart and they're not experiencing the forces of attraction. And high temperature. It's given a lot of energy so they can overcome the force of attraction and closed or nearly close to elastic collisions. Now, the butane lab review, I'm not going to go totally in detail there, but the questions that you should be able to answer to be best prepared for this test. What is the purpose of this lab? Right on the top of that sheet. What steps did you do? You should know in your mind, walking through what you did for all the parts of this lab. What data did you actually collect, and what data was given to you or did you find off of a table? And we're going to talk about that in a second. So looking at this, we have the variables there, and I said you need to be able to convert them all to their units. This is the ideal gas law, so we talked about that in an earlier slide. And where did you find each of these? So G, because the formula that you're actually using is molar mass equals GRT over PV. The reason that this works is because molar mass is equal to grams over moles. If you manipulate it so that you're just isolating moles, moles equals grams over molar mass. And N in the ideal gas law is equal to moles. So you replace that N with grams over molar mass, manipulate it, and you get this equation. Molar mass equals GRT over PV. The G is the mass of the butane dispensed from the lighter. So you mass it before and after, and you subtract it, and you get the amount of gas that was used. R is the ideal gas constant, you know that. T is the temperature of the room. Remember, this is for the molar mass of butane. You don't put the temperature of water right into the equation. The temperature of water gets used later. You use the temperature of the air of the room to get your temperature for that equation. Now the temperature of water comes in when you find pressure, because you use that temperature of the water in the table. The water vapor pressure table gives you the vapor pressure of the water, and then you subtract the pressure, the total pressure in the room, the barometer, right, the barometric pressure minus the water vapor pressure, and that gives you the partial pressure of the butane. That's the number that gets used in for P. And finally, V is the volume of the butane collected. Make sure that it's in liters. And then if we had an example here, I give you the masses of before and after for the lighter, the volume of the butane collected, the total barometric pressure, and the water temperature and the room temperature. From that, you should be able to solve for molar mass. And there's the water vapor pressure table on this slide. So if you stop the video now, do your calculations, see if you can come up with the right answer, and then I'll continue in a moment. All right, I'm assuming you've done this. If you do all that, hopefully you got 61.02 grams per mole. And if I did it correctly, 61.02 grams per mole. Great. We've done it. We have a value now. Is that the right value? Well, the actual molecular formula for butane is C4H10. And if we do that, then the theoretical mass, the theoretical molar mass would be 58.14. Our experimental or observed would be 61.02. To find percent error, it's theoretical minus experimental or experimental minus theoretical divided by theoretical. Absolute value. So it doesn't matter if it's negative, it's going to be positive. You're going to make it positive times 100. And if you do this calculation, I'll stop for a moment to see if you can get the right answer. Okay, if you checked it, and then hopefully you should get, oh no, it didn't come out. It's like I'm so sorry, it's about 4.65 or 4.95. Do I have it on my calculator still? 4.95%. Somehow I didn't put it on there. 4.95%, so I'll make sure I get it on there. All right, essential skills review. Now I'm just gonna briefly go over each of the units, and you think, okay, do I know that? Do I not know that? And then you can go back to sciencegeek.net and review it. You can go back to the old review quizzes in the units and review them that way. But it's just essential skills. So in 8, the essential skills were grams to moles conversions of the same substance. If I have, 16 grams of oxygen, or let's do 24 grams of oxygen, how many moles of oxygen is that? Moles to moles conversion using the coefficients from the balanced equation. And then those are both 2-step bridges. And then finally the 4-step bridge was the grams of A to grams of B. So you should have that stoichiometric pathway of a gram to gram conversion. Unit 7 was thermo, kind of a tough one. The heat flow, remember we're talking about, the metal comes out of the boiling water into the room temperature water in the calorimeter. Which way is the heat flowing? So that's an example question of that. The phase change graph was all the questions about, hey, is it exothermic or endothermic? Bonds broken or formed? Heat gained or lost? Delta H being positive or negative? So, and then is it delta H of fusion or delta H of vaporization? So you should know those. Phase change calculations, Q equals M times delta H. And 2 questions for that one you have to know. Is delta H the delta H of fusion or delta H of vaporization? And is it going to be negative or positive? Specific heat calculations, Q equals M times CSP times delta T. And the delta T, of course, is the T final minus T initial. CSP being the actual specific heat. So you might have to solve for Q, which is just heat, or you might have to solve for one of the other variables. Unit 6 was reactions. You had to balance the reactions. Then you had the 5 types of reactions. So single replacement, double replacement, synthesis, decomposition, and combustion. Combustion is one kind of tricks a lot of people. And then Le Chatelier's principle. So if you have a ruler or a pencil, remember that it's, if you increase the concentration of a reactant, which way will Le Chatelier, which way will the equilibrium shift to get back to equilibrium? In that example, it will go more towards the products. So you have to make sure you have that. Unit 5 was molecular geometry. You don't have to know the trigonal, pyramidal, those ones, but you do have to know about the intermolecular forces. So, the states of matter dance, solids, liquids, and gases, that the strongest intermolecular forces are the solids and the weakest are the gases. They're far apart. Biological molecules form covalent bonds. That's because we're mostly made of non-metals. And so when we combine, we make covalent bonds. Carbon is the backbone because it can form 4 bonds. Of biological molecules, it can form 4 bonds, the most bonds. And then the different types of intermolecular forces. Ionic is the strongest. Dipole is next, and actually hydrogen bonding is a very strong form of dipole bonding. Dipole bonding is between between polar molecules. Polar molecules make bonds there. And then London dispersion is the non-polar because it's very weak. Unit 4, more about the bonding, but that was the ionic, covalent, metallic, and what type of elements make each of those. And being able to draw a Lewis dot structure, or at least be able to identify the correct Lewis dot structures. Remember that every element or atom in a Lewis dot structure has to have 8 electrons around it, except for hydrogen, it can only have 2. And then Unit 3, dimensional analysis. This was a tough one. You have to be able to define a mole, the amount of a substance that is contained in exactly 12 grams of carbon-12, something along those lines. And then moles to atoms conversions, and this is where this part of the definition of a mole is 6.02 times 10 to the 23rd atoms, or 6.02 times 10 to the 23rd molecules. That's a 2-step bridge. Then between grams and moles, using the molar mass, that's a 2-step bridge. And then finally between atoms to grams, that's the 3-step bridge. Unit 2 is the periodic table in chemistry math. So the families, alkali metals, alkaline earth metals, transition metals, metalloids, halogens, and noble gases. Being able to identify if elements are metals, non-metals, or metalloids. Knowing the difference between ionization energy, electronegativity, and atomic radii. The definition of the trends and which way the trends increase or decrease on the periodic table. Also, being given the molecular formula, you can find the number of atoms, the number of molecules, and the molecular mass of those formulas. And finally, Unit 1 was the atoms. There's a lot of essential skills here. If we gave you an element from the periodic table, you need to be able to know the average atom, how many protons, electrons, and neutrons, give its atomic mass, tell us how many valence electrons there are, you kind of draw it, be able to identify the electrons in each energy level. Know that the mass of the atoms in the nucleus and the volumes in the electron cloud. Know that the nuclear binding force is stronger than the electromagnetic repulsion in the nucleus. The protons want to push each other apart, but the nuclear binding force holds them together. Know that fusion energy is stronger than fission energy, which is much stronger than chemical energy. And fusion is what you find in the sun. The fission is what happens in nuclear reactors. And then chemical energy would be like a burning log. And then finally, I'm not quite sure if this was an essential skill, but it's up there just in case. Alpha is the largest particle. This is the different types of radiation. When an atom decays, it can give off alpha radiation, which is a helium nucleus. It can give off beta radiation, which is an electron. It can give off gamma radiation, which is just an energy wave. The alpha particle is very large, but it doesn't go very far. The beta particle is an electron. It goes a little bit further. The gamma being just energy, it just goes through a lot of things. It causes the most damage. And I believe that's all of it. So, if you should have any questions, please email, but I suggest that you obviously study your notes, get those down, solidify the things that you understand, and especially those essential skills. And then if you have time, you should, if you can, make some time to go back and review some of the essential skills that when we went over them, you said, I don't remember that. That's what you should be studying. All right, guys, we'll see you all in the next couple days.